All right, guys and gals, today we're going to be looking at something called the hinge theorem. All right, this is going to be inequalities involving two triangles, and we're in chapter 5, section 5. Basically, what this deals with is the idea, let's say I had a triangle here and a triangle here, and let's assume these sides are the same and these sides are the same. And it's based on the idea of side, angle, side. And here's sort of the gist. It says, look, if I've got two triangles, and we'll finish them off here in a minute, but if we've got two triangles who have a side, angle, side relationship, and one of these triangles has an angle that's greater than the other, then that means this triangle, this side, is greater than this side. So for example, let's say that this angle is, I don't know, just eyeballing that, let's say it's 70 degrees. All right. And that this triangle over here, again, just eyeballing it, maybe it's 30 degrees. All right. Again, a side angle side relationship, so side included angle side. If we have that and this angle is greater than this angle, then it means this side is greater than this side. And that makes a lot of sense, and that's why they call it the hinge theorem. If we pretend that this is a hinge, say like of a door opening or closing, obviously the more we have that door open, the wider the distance is from the end of the door to the door jamb. Same here. Again, if I only open the door a little bit, the distance from the door to the door jamb is much smaller. So when you see all the technical writing here in a minute, that's basically what they're telling you. All right. So take a look. Here's all the technical mumbo jumbo. And again, we'll go over it. It's not very complicated. Sometimes it's referred to as the side angle side inequality theorem. I like calling it the hinge theorem. It just kind of helps remind you what it's really about. So here's what it says. Look, if two sides of a triangle, so here are our two triangles, if two sides of a triangle are congruent to two sides of another. So in this case, we know that AB, this side here, is congruent to PQ, this side here, and that AC, this side here, is congruent to PR, this side here. It says, and the included angle of one triangle, okay, is greater than the measure of the included angle on the other. So in this case, angle 1, okay, is that greater angle than 2. Then the third side of this first triangle has to be longer than the third side of the second triangle. So in other words, BC has to be greater than PQ. So again, it's all based on this idea of, say, a door opening or closing. Again, notice if this is the doorway and here's the door, if I open that door wider than, say, I did here, then the distance from the end of the door to the door jamb has to be further than, say, the distance from the end of the door here to the door jamb at R. So let's see if we can work this out. So for example, here's a diagram. We're trying to figure out what's the relationship between AB, so this segment here, so let's see if we can make it a little bit darker to see it, and CD, all right, this segment over here. All right. Well, take a look. I noticed that these two triangles have DB in common, so I'm going to mark that. I also noticed that CB is 15 units, AD is 15 units, so these are the same. And if I look, angle ADB is only 20 degrees. So I'm going to write that in so I can see it a little bit better in terms of where it is on the triangle. This side, DBC, is 50 degrees. Well, since 50 is greater than 20, that means CD has to be greater than AB. So that's what I'll write. I could write it as CD is greater than AB. Of course, I could also write it the other way around, right? I could also write that AB is less than CD, and either one of those answers would be correct. So heads up there. All right. This go around, let's use that same idea and see what we can do to write an inequality to figure out what are some possible answers. Here we know simply that one is greater than the other, but this is going to give us some possible values for that value x so that we can know potential side lengths. So take a look. This is an equilateral triangle. I know that because all three sides are the same, so that means all the angles are also the same. All right. So that means we've got 60 degrees here, we've got 60 degrees here, we've got 60 degrees there. So let's look. I've got side and side. These are the same as all of those sides. I notice that this side length is opposite 60, whereas this side length is opposite 45. So that means since 60 is greater, x plus 5 has to be greater than 3x subtract 7. Again, notice this 3x subtract 7 is across from only a 45-degree angle, whereas this x plus 5 is opposite a 60-degree angle. And notice the sides that they share are all equal. So from there, let's go ahead and see what we can do to solve. So I'm going to subtract x on both sides. So that's 2x subtract 7 is, let's see, we got 5 here. And then on the other side, we'll go ahead and add 7 to both sides. So that's 12 is greater than 2x. We'll go ahead and divide on both sides. So that means 6 is greater than x, or another way of saying it is that x has to be less than 6. So long as x here is less than 6, then whatever values we come up with would work. Now, obviously, since we're talking about a true geometric figure here, obviously we wouldn't want our side lengths to become less than 0. All right. So for example here, I couldn't let this side, for example, I don't know, let's go ahead and make it 0. If I make that x a 0, 3 times 0 is 0 times, or subtract 7 is negative 7. Well, we can't have a negative 7 side length. So obviously there would be some constraints on the other side. But for our purposes, x being less than 6 is fine. Obviously, we'd want real number, or not real number, but positive number answers for these side lengths. That's something we'd have to keep in mind. All right. So on we go. Now this, yep, there we are. So this is known as the side-side-side inequality theorem. Personally, I like to think of it as simply the converse of the hinge theorem. In other words, we're going to do it in reverse. So take a look. This go around, it says, look, if two sides of a triangle are congruent to two sides of another. So again, we've got AB and PQ being the same. And we've also got AC and PR as the same. It says, and the third side in one triangle is longer than the third side in another. So notice this time we don't know anything about angles. We only know the three sides. So in this case, I know that BC is greater than QR. So I'm going to give BC a distance here, just an arbitrary distance. We'll say 10. All right, and then QR has to be something less than that, so I'm going to give it an arbitrary distance. We'll call it 8. All right, again, just to give it a measure. It says, then look, then the angle between the pair of congruent sides in the first triangle, so this angle here, the angle between the two congruent sides, has to be greater, so this angle has to be larger than the corresponding angle of the second triangle. And again, think of it as a door. We're calling it the hinge theorem for a reason. In this case, the converse of the hinge. So again, if I know the distance of the door jamb, if I know the distance, how long the door is, and I know that I've opened from the door jamb to the edge of the door, say 8 feet, well then, cool. I know this angle is smaller than this one, whereas if the distance from the door jamb to the door is 10 feet, well, cool. That means I've opened the door wider. So notice this is going in reverse. Instead of knowing these angles and being able to say something about the sides and how they compare, here I know all three sides, and that lets me know something about that opposite angle. In this case, the measure of angle 1 being greater than the measure of angle 2. So let's try it. So I notice in this case that SQ is the same for both of my triangles. And we're going to do the same thing here. We're going to try to compare these two measures. So SQ is the same in both. I notice also that sides QR and QP are the same. So I'm going to go ahead and mark those just to make it a little easier. So these are the two angles in question. We've got PQS, so we'll call it angle 1 just to make it easier to see. And then we're also looking at RQS, we got angle 2, again, just to make it a little easier to see. Well, obviously, angle 1 is across from an 8-unit side, whereas 2 is across from a 6-unit side. So that means that angle 1 has to be the greater of the two. So PQS has to be greater than RQS. Let's write that out. So the measure of angle PQS has to be greater than the measure of angle RQS. And of course, the reverse is true as well. We could also say the measure of angle RQS is less than the measure of the angle PQS. And again, either one of those answers would be deemed acceptable. Obviously, if it's a multiple choice situation, say on a quiz or something, I might only show one or the other. So you would need to know that both could work. But again, either one of those answers, say in a short answer situation, would be acceptable. All right? So let's try some quick examples here just to make sure we're all comfy cozy. I grabbed these out of our textbook that's online. So again, if you're wanting to look up extra problems or that kind of thing, remember those are out there. I think it's odd numbered answers are in the back of the book. So again, if you look for that section online, you can find answers pretty quickly. So let's take a look. So in this case, we're asked to write an inequality relating the given pair of angles or segment measures. So let's notice, in this case for AB and FD, so AB is here, FD is here. I notice that they share this side 6 in common. These sides 9 are the same. So let's see here. Oh, I did it backwards, didn't I? Not AF. Oh, goodness gracious me. Helps if you can read. Let's see. AB, we're comparing that side. And FD, this side. No, I had that right. FD. So this side we're comparing. Let's make that dark. This side we're comparing, make that dark. Again, guys, with some of these, you want to make certain that you are paying close attention. So we've got a 6 and 9. We've got a 6 and 9. So we're looking at AB to FD. So again, it should be kind of obvious. They're measured out for us. So AB being 9, FD being 6. So we could write that out as AB. Make sure I'm writing that correctly. Is greater than FD. So 6. So FD. Pretty cool there. Let's see what else we've got. Measure of BD. Oh, where is D? BDC. So this angle here. Actually, I'm going to erase those so I don't make a mess of it. There we go. So the measure of BDC, so this angle here. The measure of FDB, so this angle here. So these are our two in question. And let's see what we can figure out. Well, I noticed that these two triangles have this 9 side in common. They also have this 6 side that are the same for both. Angle FDB is opposite a side that is 6, whereas CDB is opposite a side that is only 4. So this FDB side is greater. So I can say the measure of angle BDC is less than the measure of angle FDB. And again, we could say the opposite is true as well. We could say the measure of angle FDB is greater than the measure of angle BDC. But again, I'm going to keep it in the order in which it's written here. All right, let's erase those again. And guys, it helps sometimes if you draw these out, maybe you only draw a portion of the image just to make it easier to see what's going on. So we've got FBA, so this angle here, and we've got DBF, so this angle here. I notice that these two triangles have the sides 6 in common. They've got the sides 9 in common. And again, just like we related up here, this angle is opposite 10, whereas the FBD is opposite only 6. So ABF, or FBA as they call it, FBA, this angle is greater than the measure of angle DBF. All right. Well, let's try the opposite. Again, we'll still write that inequality relating what's going on here. So we've got AD that we're looking at. So this side here. And DC, where is DC? DC, this side here. And let's see what we can figure out. I'm going to ignore this line and pretend we've got triangle BDC and BDA. So again, I'm going to ignore this line for a moment. Notice they've got this side plus this side. So BD is obviously the same for both triangles on the left and right. They also have side 8 on both sides. 60 is opposite this side, which is going to be longer than the side opposite the 40. So DC has to be smaller. So AD is greater than DC. So in this case, so long as DC is something less than 8.11, then we're good to go. All right, so if we're wanting potential answers for that or potential side lengths for CD, as long as it's less than 8 and 1100ths, it should work based on the information we know at this point. All right, let's look for OC. So I'm going to erase those. OC is right here. And OA, so this side right here. And again, it's kind of the same setup, but instead of looking at this whole triangle, I'm only going to look at the smaller version. They have this side in common. They've got these sides 8 in common. Again, 60 goes to here, 40 goes to there. So AO or OA has to be greater. So OC is less than OA. All right, it's pretty straightforward, not too bad. Again, it helps if you block it off or redraw the diagrams. That way you can see exactly what you need. All right, now we're going to look at angles. So angle AOD, so this angle here, AOD, and we're going to compare it to AOB, so this angle up here. Let's see what we can figure out. It looks like they share this side in common. Let's see now. In this case, let's see, I'm going to make the triangle a little darker here. Well, in this case, it's going to be tough to tell. We know that 8 is opposite here and 8.11 is opposite here. The issue I'm having is that we don't know what this side is. Now, take a look. They've got AO in common, so that looks good. We would need to know that BO and DO are the same size. In this case, we know that we've got 3 here, but we don't know anything about what this side is here. In order to do what we need to do, we need to know that 2 sides are indeed the same. In this case, since we don't know that, I'm not 100% certain that we could tell anything exact. Let's look. We know they've got this side the same, but 8 and 8.1 are different. Yeah, in this case, I was going to say there is not enough information as given. However, let's pretend that from O to B is also 3 units long. If we know that, then it should be very obvious. In this case, we've got an 8.11 versus an 8, so AOD would end up being greater in that case. So let's write that out. If BO is equal to 3, then we could say that the measure of AOB, right, is going to be less. So we could say the measure of angle AOD is greater than the measure of angle AOB. But again, unless we know that side's 3, there's really not enough information for us to work on. So again, sometimes we will run into that. We just don't have enough information to make a good assessment. Otherwise, we could assume things. In this case, if BO is indeed 3, then cool, we can make that statement. So again, today we'll be working with the hinge theorem. It shouldn't be anything too drastic. Again, if you find diagrams, there we are, like that are just too darn complicated, well, again, only draw certain parts or grab you another sheet of paper, cover them up, and that way it makes it just a little bit easier to work with it. You're only looking at certain triangles and not trying to deal with the whole thing. All right. If you have any questions or concerns, make sure you ask them during class when we meet up. Otherwise, have a good day, guys and gals.